Today we're talking about section 3.2. 3.2 talks about polynomials and their graphs. So we have quite a few objectives today, but usually when we have a lot of objectives like this, they're relatively simpler. So strange. You're so strange. Relatively simpler objectives. Okay, so let's go ahead and get through some of these. Identifying if something's a polynomial or not. Okay, recognizing characteristics of graphs of polynomial functions, determining end behavior, using factoring to find zeros of polynomial functions, identifying zeros and their multiplicities, using the intermediate value theorem, understanding the relationship between degree and turning points, and graphing polynomial functions. Okay? You ready to get started? So if we're going to identify a polynomial function, we have to know what a polynomial function is. Okay? If I give you a sample, like f of x equals negative 3x to the fifth plus the square root of 2x squared plus 5, I need you to be able to look at that and tell me either yes or no. Yes, it's a polynomial function, or no, it's not a polynomial function. Okay? So, just for the record, the definition of a polynomial function reads like this. Let n be a non-negative integer, and let a sub n minus 1, a sub n minus 2, a sub 2, a sub 1, and a sub 0 be real numbers, where a sub n is not equal to 0. So then this function, f of x equals a sub n x to the n plus a to the n minus 1 x to the n minus 1 plus plus a sub 2 x squared plus a sub 1 x plus a sub 0 is called a polynomial function of degree n. Now notice right here, that's the degree, and it's the highest exponent in the polynomial. Okay? The number a sub n is the coefficient of the variable to the highest power. This a sub n right here is called the leading coefficient, because once the exponents are in order from greatest to least, this coefficient right here is the leading coefficient. It's the first one. Okay? So you've got to be able to look at something like this and tell if it is a polynomial or not. And really a lot of it has to do with what kind of exponents we have. Okay? There's a 5, there's a 2, there's nothing right here. So first thing I want you to notice, and we're kind of jumping around a little bit on our objectives because this is more of a characteristic, but this polynomial has a degree of 5. Okay? And when you can determine what the degree is, then you know you have a polynomial function. So this one is a polynomial function. It's a yes, and the degree is 5. Okay? F of x equals negative 3x to the 1/2 power plus 2x squared minus 5. Is that a polynomial function or not? That is not a polynomial function because of that exponent right there. Okay? So basically we're going to have whole number exponents to determine whether we have a polynomial or not. Okay? F of x equals negative 3x to the 6th minus 3x to the 5th plus 18x to the 4th. Is that a polynomial function or not? Yes, correct. Can you tell me what its degree is? Its degree is 6. It's the highest exponent. Okay? One more, just so we have it. F of x equals negative 3x to the negative 2 power plus 4x squared minus 18. Is that a polynomial function or not? Why? A negative exponent? That's a no. It's not a polynomial. Okay? Any questions? You can also tell by looking at the graphs if it's a polynomial or not. Okay? I'll give give you a couple graphs, and we'll draw some stuff. And you can know if they're functions or not. Okay. Is that a polynomial function or not? Yes, it is. Notice right here and right here, those are smooth, rounded corners. Okay? They're smooth. I said corners, I didn't mean corners. Can I take that back? Curves. They're smooth. There's no sharp turns. And another thing is that they're continuous. Now, if you'll remember, that was a little bit of an issue that we had last year, determining the difference between continuous and continuing. Guys, those are two different things. The arrows on the end mean they're continuing, okay? But they're continuous because they're connected. See? Continuous, connected. The whole thing is connected to each other. There's no breaks, there's no holes, anything like that. Okay? So that's connected. So that is a polynomial function. What about this one? Is that a polynomial function? No. Why? It's not connected. It's discontinuous. Hold on. Continuous. It's smooth right here on this part and on this part. That's true. But there's a break right there. That's not a polynomial curve because it is discontinuous. Okay? What about that one? Why? Why is it yes? It's smooth and it's continuous. Okay? No? Why no? Not smooth. There's sharp corners right here and right here. Okay? Any questions about that? So can you identify a polynomial function either from a graph or from an equation? Okay? End behavior. So we did really number 1 and number 2 together, recognizing characteristics of the graphs of polynomials. That was mostly the smooth and continuous right here versus the sharp or not continuous, discontinuous curves, okay? So the next thing on our objectives is determining end behavior. That means what's happening at the end. I want to start with a parabola because that's the easiest one to talk about. It's the one you're most familiar with too. Okay? End behavior means what's happening at the far left and what's happening at the far right. Okay? What's happening at the far left of this curve on the left, it's increasing or rising. Okay? What's happening on the right? It's rising. Or rises, I guess is what it says in your textbook. It rises. Okay? And that is for y equals x squared, right? Now, that's not the parent function, so it's only kind of like this because I didn't put it in the right place. Okay? But then you also have a cube root curve, which looks like this. So y equals x to the third. Okay? What's happening on its left? Falling. Or it falls. What about its right? It rises, right? Okay? Now, what we're going to need you to be able to do is talk about the end behavior of an equation without looking at the graph. Okay? So, in any particular function, we're going to be able to tell the end behavior by looking at the leading coefficient and the degree. Okay? Now, remember the degree is the highest exponent. And we're going to talk about LC. I'm just going to abbreviate it like that. We're going to talk about the leading coefficient. Okay? Now, if our general form of our function is what I wrote just a second ago, but I'll write it here again so you can see it. F of x equals a sub n, x to the n, plus a to the n minus 1, x to the n minus 1, plus dot, 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 plus a sub 1, x, plus a sub 0, okay, where we know that a sub n is not equal to 0. That wouldn't be any good, okay? The first thing I want to talk about is n. Notice what we're calling n here. That's the degree, okay? When n is odd, I don't know why I wrote my is so far apart. I'm sorry about that, okay? When n is odd, so like this, okay? See how the 3, that's an odd number, okay? When n is odd, tell me about the n behaviors. They're going to be opposite, right? The n behavior is going to be opposite. When the degree is odd, the n behaviors are going to be opposite. So if I could figure out one, I would automatically know the other because of the fact that we know that those are opposite, okay? When n is opposite, if the leading coefficient is positive, the graph falls to the left, okay? So when n is odd, when the leading coefficient is positive, then it's going to fall to the left. Like this. My degree is odd. My leading coefficient in this case is just a 1. That's positive. It's going to fall to the left. Well, since I know that the behaviors are opposite, what's happening to the right? It rises. Okay? So when my leading coefficient is negative, then what's going to happen to the left? It's going to rise to the left. Now, we also talked about the fact that if my leading coefficient is positive, it's going to fall to the left and rise to the right, because I know that my behaviors are opposite. If my leading coefficient is negative, it's going to rise to the left and fall to the right. Okay? So what's going to happen when n is even? What about when my degree is even? Tell me about the n behaviors. N behaviors are the same. God bless you. So when n is even, I know my n behaviors are the same, so I can figure out one and know the other one because I know they're the same. Okay? If the leading coefficient is positive, when n is even, if the leading coefficient is positive, the graph rises to the left. Which means it also rises to the right, because I know they're the same. If the leading coefficient is negative, it's going to fall to the left, which means it's going to fall to the right. Now, sometimes I have to look up the rules when I have to actually say the rules. I know the rules because I just compare them always back to these two. These are two functions that I've talked about for a long time. You guys have talked about it for a long time. Not as long as me, but that's a different story. Okay? Parabolas, I know, have a degree of 2. That's an even degree. They're going the same direction. I know because of my studies of parabolas that if it's opening up, the leading coefficient is positive, and if it's opening down, the leading coefficient is negative. Does that make sense? So I also know because of the cube root, that's an odd that they're going opposite directions. I know a parent function falls to the left, which means the leading coefficient falls to the left. Does that make sense? They are. Well, y equals x looks like this. So that doesn't have a variable. So that doesn't have an exponent. So yeah. Horizontal lines, it doesn't really work for this because we're mostly talking about something with a degree, something with an exponent, and now it doesn't have an exponent. Well, its exponent is 0, and 0 is not odd or even. So, does that make sense? Okay. How are you guys feeling about the end behavior stuff? Sleepy? That's fair. I also am feeling sleepy. It's right after lunch. Okay? Should we keep going or should we stop and take a nap? That was just a rhetorical question, just for the record. Okay? Because I actually know what your answer would be because it's the same as mine. Okay. So, next we need to talk about factoring. Okay? Now, have we talked about factoring in here since we started college algebra? Have we done factoring? Okay, I'm just confused because we're doing a lot of factoring in regular algebra now, so I couldn't remember if we had already done it in here or not. There's a ton of different types of factoring. Even in the book, there's not a whole bunch of examples for factoring, which is why I was thinking we had already done factoring. So if you can just do regular factoring, should I go over the AC method again real quick for trinomials? That's usually the ones that you guys struggle with a little bit. Let's do 6x squared minus 13x minus 5. Do you remember how to do AC method on a trinomial like this? Find AC. What is AC? Negative 30. It's A times C. And what's B? Negative 13. So what two numbers multiply to be negative 30 and add to be negative 13? What? 15 and 2? What kind of 15 and what kind of 2? Negative 15 and positive 2, right? Okay. So remember, I'm going to split the middle term into two parts. These two parts that I just figured out. 6x squared minus 15x plus 2x minus 5. Also remember, this is not the only way to do this. This is just kind of how we went through it and talked about it in Algebra 2. Okay. Now we factor by grouping. What's common in the first two terms? They're both divisible by 3x, right? What's left if I divide both terms by 3x? 2x minus 5, right? What's common in the second two terms? Knowing I have to factor something out. Just a 1, right? What's left if I divide each of these two terms by 1? Well, 2x minus 5, okay? So this is a term now, and this is a term now. Do these two terms have something in common? They both have a 2x minus 5, right? So if I factor out a 2x minus 5 from each term, what's left? 3x plus 1, right? 3x plus 1. So even if there's nothing to factor out, you have to factor something out so that we can do the AC method. Yeah. Okay? So this is what this is factored. And the only thing really that's right here, number 4, use factoring to determine zeros of polynomial functions. The only thing that's different in these kind of problems is the fact that it's going to be like this, equals 0. So all these are equals 0, equals 0, equals 0. And if you have two things like this that are multiplied together that equal 0, what has to be true about one of them? One of these two has to be 0, right? That's the only way you can multiply two numbers and get an answer of 0 is if one of them is 0, okay? Well, which one is it? Well, I don't know either, okay? So we have to take into account what if they both are. We have to take both possibilities. So we set each one of these factors, 2x minus 5, equal to 0. 3x plus 1 equals 0. So we're finding the zeros of this polynomial right here by factoring and then setting each factor equal to 0. And now we're going to solve each factor to find the value for x that makes that equation equal to 0. Same thing here. Dividing by 3 on both sides gives me x equals negative 1/3. And these right here, these values right here, are my zeros. Okay? These right here are my factors. These two, those are my factors, but these are the zeros that come from those two factors. So it's just remembering all the factoring rules that we talked about before to factor to find the zeros of the polynomial. Okay? Now, identifying zeros and their multiplicities, that really has a lot to do with factoring if you need to, but it really, you can really find multiplicities a lot easier by looking at the graph. And keep in mind that the fundamental theorem of algebra says that the number of, the degree is how many solutions you should get, right? So if I solve this and I got 2 answers, so I found all the answers that are possible, right? Well, sometimes I might have a multiplicity, which means when I get all the way factored down, I get this. Now, according to the problem, if I multiplied this out, this would start with an x cubed, right? So I've got my 3 factors, but if I solve each one of these, I'm going to get x equals negative 1, x equals negative 1, and x equals negative 5, aren't I? So if I go to write my answers, I've got x equals negative 1 and x equals negative 5. I don't really have to write negative 1 twice, except if I just write it like this, it looks like there's only 2 answers, and I need 3. Okay? So obviously one of these answers has a multiplicity. That means it happens more than once. And you can tell those when you look at the graph. If you have your graph and it looks like this, okay, pretend that just stops right there, like 1, 2, 1, 2, 3, 4. Okay? Notice that it reaches down and touches negative 2, but doesn't pass through it. It goes back up. Chances are there's a multiplicity of negative 2. It's going to be the negative 2 and negative 2 like this is right here. Okay? And this is going to be a 4. That's only going to happen once because it goes all the way through the graph right there. Okay? You can tell multiplicity is pretty simple if you can see the graph because it's just changing directions. And that's where the multiplicity is going to happen, as opposed to passing through the x-axis. That's only going to happen once. Okay? Although sometimes you're going to need to, you might be able to tell the multiplicities given the equation, because you might have an equation or a function that looks like this. Well, my general problem, my beginning problem is going to start with x to the 5th, so I know I need 5 solutions. But look at this one. X equals negative 4 from here is going to have a multiplicity of 2. It's going to change directions right there at the negative 4, okay, on the graph. This x equals 5 is going to have a multiplicity of 3, because that exponent right there is telling me I have a multiplicity of 3. Does that make sense? Any questions about that? So, identifying zeros and their multiplicities. You got that okay? At least for now. If not, we can always talk later. Okay? Then there's the intermediate value theorem. Okay? Intermediate value theorem is pretty important. Okay? Let me get a new piece of paper for that. Intermediate value theorem. So we're going to let f be a polynomial function. F is a polynomial function. Okay? F of A and f of B have opposite signs. So if f of A and f of B have opposite signs, like the value of the function, if I plug in A, the value of the function, if I plug in B, if they have opposite signs, there is at least one value, we're going to call that C, between A and B, where f of C is 0. So if I'm talking about a graph, and it's like that, and I'm talking about this point, and we'll call that A, so that value is f of A, versus this point, we'll call this is B, so this is f of B. Does it make sense that there's a value that we can call C in between there? Since this one is a positive and this one's a negative, there's at least one value in there where it crosses the axis. So the value is 0. That's what the intermediate value theorem says. That's all it is. Okay? Any questions about intermediate value theorem? I need to do an example for you, or just let you work on your stuff and ask questions if you need to? Yes? Okay. Understand the relationship between degree and turning point. That's something that I can't do for you. Okay? I can show you some examples, but I cannot understand it for you. So I just think that's an interesting objective, because I want you to understand it, but I can't do it for you. You know what I'm saying? So, turning points, it's a really simple concept. Okay, if I have f of x equals x to the 5th plus 6x to the 3rd plus 8x plus 1, whoa, and I'm going to tell you the graph looks something like this. And those are all supposed to be nice curvy points because it's a polynomial. Sorry about that. Okay? The graph looks something similar to that. What is the degree here? 5. How many turning points or turning places are there on the graph? 1, 2, 3, 4. How is the degree and the turning points related? Always? Is the number of turning points always one less than the degree? Yes. Okay? Again, that's something that I think back to this for. This is a quadratic. I know its degree is 1. 2. I know it turns once. This has a degree of 3. I know it turns twice. Once here and once there. You know what I'm saying? I refer back to it. I don't always remember the rule. I remember general things, and I can figure out the rule from the general things that I know. Okay? So all that's left is graphing them. Well, we have calculators we can use. We can find the intercepts, the zeros. We can find the y-intercept if we let x equal 0. We can know how many turns it makes, and we can actually graph it without a calculator, can't we? Okay? We know if things have a multiplicity of 2, it's just touching on the graph right there, like we talked about right here. If it's a multiplicity of 2, it's just touching and going up. If it's a multiplicity of 1, it's going right through that spot. So we can actually use all the stuff we talked about today and actually graph something that's generally the same shape as the actual graph without actually seeing the actual graph on the calculator. Okay? And that's really what it's asking you to do. Because if it just says, like, literally graph a polynomial function, we're going to use a calculator. Okay, but if it wants you to graph it based on the end behaviors, the intercepts, the other things that you know, the characteristics about the stuff, you can totally do that. Okay, that's all our objectives. How do you feel about these? Do we need to go back over any of them? Are you good? You just want to start working so you can ask questions as you go along? That's perfectly fine.